The meteorologist was on his third cup of coffee at 2 in the morning when the model output came in from the latest data assimilation cycle, and the number in the intensity forecast column stopped him mid-reach for the mug. He had been running these overnight shifts at the Joint Typhoon Warning Center for 7 years, had processed the full range of what the Western Pacific produces across every month of the calendar, and had developed the specific professional composure that comes from watching major typhoons form and intensify and make landfall with enough regularity that extreme weather becomes, at some level, ordinary. The number in the column was not ordinary. It was the projected central pressure at 72 hours, the 3-day intensity forecast for the system that had been designated as a tropical depression 36 hours earlier, and that the morning consensus had assessed as likely to develop into a moderate typhoon by the end of the week. The number in the column was not the number for a moderate typhoon. It was a number he had seen printed in intensity forecasts perhaps a dozen times in 7 years on the night watch, and each of those times the forecast had been for a system that was already a significant typhoon showing signs of exceptional intensification. This was a forecast being produced for a system that was still organizing. He pulled up the satellite imagery loop, the sequence of infrared images that showed the storm's cloud structure evolving over the past 12 hours. The loop confirmed what the model was suggesting. The convective organization around the storm center had advanced markedly in the past 6 hours beyond what the afternoon trend analysis had projected. The deep convection, the towers of cloud reaching to the upper troposphere that are the engine of tropical cyclone intensification, had tightened into a more symmetric ring around the developing center. The upper-level outflow, visible in the water vapor imagery as a spreading fan of cirrus cloud being ejected away from the storm's core at altitude, was expansive and well-organized in all quadrants. The storm was doing something that the models, which had been producing moderate intensity forecasts as recently as 18 hours earlier, had not fully anticipated. It was finding the most favorable atmospheric state it had encountered since the first organized convection appeared over the warm water of the Western Pacific, and it was responding with a kind of rapid structural development that meteorologists call explosive intensification when they are being informal about it, and rapid intensification when they are writing the official forecast discussion. He updated the forecast and sent it through the required review channels. He wrote a sentence in the forecast discussion that he later described as the most understated thing he had ever written in his 7 years on the night watch. The sentence read, "The system is exhibiting early signs of intensification that exceed current operational model guidance and warrant close monitoring. By the time the day shift arrived at 6 in the morning, the system had completed its first 12-hour period of sustained rapid intensification, increasing its maximum sustained winds by 35 knots during the overnight hours." The forecast discussion that accompanied the morning update did not use the word understated. It used the word alarming, which is not a word that appears often in official meteorological communications, and the senior forecaster who reviewed it before it went out considered changing it and then decided to leave it because the evidence in front of her suggested that alarming was the correct and honest characterization of what the data was showing. The Western Pacific Ocean in the region where the storm was developing is not an unusual location for major typhoons. The Western Pacific generates more tropical cyclones than any other ocean basin, fueled by the warm, deep waters of the Pacific Warm Pool and by the favorable atmospheric conditions that persist through much of the year in the region. Typhoon season officially runs from June through November, with peak activity in August and September, and the basin produces between 25 and 30 named storms in an average year, a substantial fraction of which reach typhoon intensity of 64 knots or greater, and a significant number of which reach major typhoon intensity of 100 knots or greater. The forecasters at the Joint Typhoon Warning Center and at the Japan Meteorological Agency and at the Hong Kong Observatory and at the other national meteorological services that monitor the Western Pacific have seen many major typhoons, have tracked their development from tropical disturbance to major systems, and have developed the professional knowledge and the institutional infrastructure to monitor and forecast their behavior with increasing skill. What the current system was doing was not simply being another major typhoon. It was intensifying at a rate and to a level that was, in the context of the meteorological record for this part of the Pacific and this part of the calendar, genuinely unusual. The season was not at its peak. The ENSO conditions were not in the strongly El Nino state that had historically been associated with the most extreme Western Pacific typhoon activity. And the specific location of the system at the time of its rapid intensification was not in the region of the warmest sea surface temperatures, where the most extreme intensification had previously been observed. All of the standard factors that meteorologists use to assess the likelihood of extreme intensification were suggesting a moderate event, and the system was responding by producing an extreme one. The explanation for this discrepancy, which the meteorological community has been working to understand in real time as the storm has intensified, points toward features of the current atmospheric and oceanic environment that are less prominent in the standard forecasting frameworks, but that are producing an unusually favorable combination of conditions for extreme intensification. The upper level wind shear in the region, the change in wind speed and direction with altitude that is one of the most important environmental factors in tropical cyclone development because high shear disrupts the organized convective structure of developing cyclones, was anomalously low, lower than the standard model of the regional circulation would have predicted for this time of year. The low shear was not the product of a single large-scale circulation anomaly, but of the simultaneous alignment of several aspects of the atmospheric state, each of which individually might have produced a modest reduction in shear, but whose combination produced a synergistic reduction that was larger than any of them individually would have caused. The second factor, which is the one that the forecasters found most surprising in its magnitude, was the ocean heat content in the region of the storm's development. Sea surface temperature is the parameter that operational forecasting has historically used as the primary indicator of oceanic support for tropical cyclone intensification. And the sea surface temperatures in the storm's vicinity, while warm, were not at the extreme levels that would typically be flagged as exceptional. The subsurface heat content, the warmth of the water below the surface that matters, because a developing typhoon stirs up the ocean beneath it and can access the subsurface warmth as it deepens the mixing layer, was another matter. The same anomaly that had been detected in the Argo float data and that had prompted the concern of the oceanographic community was now providing the physical fuel for a tropical cyclone that was intensifying in ways the models had not predicted, precisely because the models had not fully incorporated the subsurface thermal anomaly into their representation of the oceanic environment. This connection between the unusual Pacific subsurface conditions and the unexpected intensification of the current storm is one that the meteorological and oceanographic communities are now examining closely because it represents exactly the kind of interaction between oceanic and atmospheric conditions that has been discussed theoretically as a potential consequence of elevated ocean heat content, but that has been difficult to document observationally in real time. The storm is, in this sense, an experiment that the atmosphere is running on behalf of the scientific community, demonstrating in the most concrete and visible way available what happens when a tropical cyclone develops over an ocean that has accumulated heat to a depth that the operational forecasting models have not fully accounted for. Tropical cyclone intensification is governed by the balance between the energy that the storm extracts from the ocean beneath it and the energy it loses to the environment around it through the various processes that limit intensification. The primary source of energy is the evaporation of warm ocean water at the sea surface, which transfers both heat and water vapor into the storm's boundary layer and provides the thermodynamic fuel for the deep convection that drives the circulation. The primary loss mechanisms are the frictional dissipation in the boundary layer, the ventilation of warm air away from the storm's core by environmental wind shear, and the upwelling of cooler water from below the mixed layer that reduces the sea surface temperature beneath the storm and progressively limits the energy available for further intensification. The depth of the warm layer is critical to the intensification process because it determines how effectively the upwelling cooling mechanism operates. When a strong tropical cyclone moves over the ocean, its winds create a surface current divergence beneath the storm that drives upwelling of cooler water from below the mixed layer. If the mixed layer is shallow, this upwelling brings cold water to the surface relatively quickly, reducing the sea surface temperature beneath the storm and limiting the energy available for further intensification. This is the self-limiting mechanism that prevents most tropical cyclones from reaching their theoretical maximum intensity, and that makes the potential intensity the thermodynamic maximum, a ceiling that most storms approach only briefly, if at all. When the warm layer is deep, the upwelling still occurs, but the water being brought to the surface from below the mixed layer is warmer because the thermocline, the transition from warm to cold water, is at greater depth. The self-limiting mechanism is reduced in effectiveness because the upwelled water is not as cold as it would be in a shallow mixed layer environment, and the storm can continue to intensify at a higher rate for a longer period before the oceanic cooling becomes significant. This is the physical mechanism by which the anomalous subsurface heat content in the Central Pacific, with its thermocline depression of approximately 140 meters below climatological average, is providing an unusually favorable environment for the current storm's intensification. The operational intensity forecasting models that the meteorological agencies use to predict how tropical cyclones will intensify incorporate ocean coupling, the interaction between the storm and the ocean beneath it, but they do so through parameterizations that are derived from historical data on ocean mixed layer depths and thermal profiles. If the current subsurface thermal state of the Pacific is genuinely outside the range of historical conditions that the parameterizations were derived from, The models may systematically underestimate the intensity that storms developing in the current oceanic environment can achieve, because they are applying parameterizations calibrated to a cooler ocean to a storm developing over a warmer one. This systematic bias, if it exists, would produce exactly the kind of consistent underprediction of intensity that the current storm is exhibiting. And it would be expected to persist for any storm developing in the anomalous subsurface environment until the models are updated to reflect the current oceanic state. The storm is providing the first real-time test of whether this predicted systematic bias is real, and the preliminary answer, based on the comparison between the operational model forecasts and the actual observed intensity over the past 48 hours of rapid intensification, is that it is. The models have consistently forecast a slower and more modest intensification than has actually occurred. The gap between the model forecasts and the observations has been growing with each successive model run, and the models have been playing catch-up with a storm that is running ahead of their predictions in the same direction, faster and stronger at every update cycle. The communities that lie in the potential path of the storm are the dimension of the story that the meteorological community is most urgently focused on, because the storm that has been intensifying unexpectedly is not doing so over open ocean far from any population. It is intensifying on a track that the ensemble forecast models are projecting toward one of the more densely populated and more extensively developed coastlines in the Western Pacific, a coastline that has experienced major typhoon landfalls before and that has the institutional infrastructure for typhoon preparedness, but that is now facing the prospect of a storm that is significantly stronger than what the watches and warnings that have been issued for the previous 24 hours were calibrated to communicate. The watch and warning system for tropical cyclones is designed to give coastal communities as much lead time as possible to prepare for the hazard a storm represents. And the warnings issued for the current storm have been based on the intensity that the storm was forecast to achieve at landfall, based on the models that were running when the warnings were issued. If the storm arrives significantly stronger than the forecast on which the warnings were based, communities that prepared for the forecast storm may be inadequately prepared for the actual storm. The gap between the warned intensity and the actual intensity, if it is as large as the current trend in the observations suggests it might be, would be large enough to move the storm from one wind damage category to another, from a category that most well-constructed modern buildings can survive, to a category where building performance becomes much less certain and where the probability of catastrophic structural failures rises substantially. The decision about whether and when to upgrade the warnings as the storm's unexpected intensification becomes clearer is one of the most consequential operational decisions that meteorological agencies are called upon to make. And the decision involves a specific kind of uncertainty that is different from the track uncertainty that dominates public discussion of tropical cyclone forecasting. Track uncertainty is the uncertainty about where the storm will go, and it is the uncertainty that drives the size of the warning area, the swath of coastline for which preparations are recommended because the storm might make landfall there. Intensity uncertainty is the uncertainty about how strong the storm will be when it arrives, and it is the uncertainty that drives the specific guidance about the level of preparation that is appropriate. For the current storm, the track uncertainty is relatively low. The ensemble models have been showing a coherent and consistent track forecast for the past several update cycles, with the storm making landfall in a relatively narrow geographic range on a timeline that is well defined within the operational forecast period. The intensity uncertainty is high and it is asymmetric, skewed toward the stronger end of the range, because the storm's recent behavior has been consistently exceeding the model guidance in the direction of greater intensity. This combination of low track uncertainty and high asymmetric intensity uncertainty is one of the more challenging warning communication scenarios in tropical meteorology, because the geographic focus of the warning is clear, but the severity of what the people in that geographic area need to prepare for is not. The meteorological agencies responsible for the warning are navigating this challenge in real time, using the intensity trend data and the current observations to produce the most honest and most actionable communication they can about a storm whose behavior is, by the evidence of the past 48 hours, outpacing the models that the operational guidance is based on. The communication is being carefully calibrated to convey not only the current best estimate of the storm's intensity at landfall, but also the uncertainty in that estimate and the specific direction in which that uncertainty is skewed, so that the communities receiving the warnings can make preparations that are robust to the possibility that the storm will be stronger than the best estimate suggests. The meteorological community has been studying tropical cyclone intensification with increasing intensity as a scientific problem over the past 2 decades, motivated both by the operational need to improve forecasts and by the growing evidence that the most extreme intensification events are becoming more frequent in a warming ocean. the scientific literature on rapid intensification, the specific phenomenon that occurs when a storm's maximum sustained winds increase by 30 knots or more in 24 hours, is extensive and has produced a detailed understanding of the physical mechanisms involved and the environmental conditions that facilitate them. The understanding has been translated into operational tools, including the statistical hurricane intensity prediction scheme and its tropical cyclone variants for different basins, the coupled ocean-atmosphere intensity models, and the ensemble intensity prediction systems that provide probabilistic guidance on the range of intensity outcomes. Despite these advances, rapid intensification remains the most significant source of intensity forecast error in operational tropical cyclone prediction. The current operational skill for 24-hour intensity change is substantially lower than the skill for 24-hour track prediction, and the skill for predicting the occurrence and magnitude of rapid intensification episodes is particularly limited. The current storm is demonstrating this limitation in a particularly clear way. Having undergone a period of a rapid intensification that the operational models predicted would be half as fast, and that has produced an intensity already 15% higher than the model consensus from 48 hours ago had projected for this stage of the storm's development. The investigation of why the models are failing to predict the current storm's intensification with adequate accuracy is one that will continue long after the storm has made landfall, when the research community can examine the full observational record of the storm's development and compare it against the model output in detail to identify the specific physical processes that the models are not representing correctly. But the investigation that matters most right now is the real-time assessment by the forecasters who are watching the storm intensify and who are making the operational decisions about the warnings that will determine whether the communities in the storm's path have adequate time and adequate information to protect themselves. Those forecasters are working with incomplete information, as operational forecasters always work with incomplete information, relying on the instruments that can observe the storm at the temporal and spatial resolution that the observation network provides, and on the models that are running in the background as continuous guidance. The instruments are providing a clear picture of what the storm has been doing. The models are providing a less clear picture of what the storm will do next. And the forecasters are, as they always do, integrating the two sources of guidance with the professional judgment that their training and their experience and their understanding of the specific storm in front of them provides. The meteorologist who first saw the unexpected number in the overnight model output and wrote the understated sentence in the forecast discussion has been on shift through most of the subsequent development. He is not the only person who has been watching. The storm has attracted the attention of every major meteorological agency in the Western Pacific region, every university research group working on tropical cyclone dynamics, and the growing community of weather researchers and enthusiasts who follow typhoon development through the real-time data feeds that the modern observational and modeling infrastructure provides to anyone with an internet connection. The storm is not a private scientific phenomenon. It is a public meteorological event, and the gap between the model forecasts and the storm's actual behavior has been visible to the full community of people who track these things, generating the specific kind of professional and public attention that unusual events attract when the unusual character is unmistakable in the data. The history of tropical cyclone forecasting is, in a sense, the history of the surprises that have driven improvements in the science. Each time a storm has done something that the operational guidance did not predict, the scientific community has examined the event in detail, identified the specific physical processes that the models missed or underweighted, and developed parameterizations or model improvements that reduce the probability of the same failure in the future. The surprises have not stopped because the atmosphere is more complex than any model, and because the range of conditions over which the models must perform is wider than the range from which they were calibrated. But each surprise has produced knowledge that improved subsequent forecasts. The current storm is producing a surprise of the kind that is most scientifically productive because it is connected to a physical cause that is both clear and general. The anomalous subsurface heat content of the Pacific, documented by the Argo network and now being physically expressed in the intensification of a storm whose behavior the models calibrated to a cooler ocean cannot fully reproduce, provides a specific and testable mechanism for the forecast failure. It is not a random miss or an inexplicable anomaly. It is a systematic failure of models that do not fully represent the current state of the ocean to predict the behavior of a storm developing over that ocean. The improvement that this understanding motivates is specific and actionable better representation of the subsurface thermal state and the ocean coupling components of the operational intensity models, and recalibration of the parameterizations that relate the ocean's thermal structure to the intensity that storms can achieve. This kind of improvement is not instantaneous. The development and testing of model changes, the validation of the changes against historical cases, the transition from research to operations in the meteorological agencies that operate the forecasting systems. These processes take months to years. The communities that will face typhoons in the Western Pacific this season and next season will be protected by forecasting systems that are, in their ocean coupling components, calibrated to a Pacific that no longer fully exists. The systematic improvement that the scientific understanding motivates will arrive, but it will arrive after the current storm has made landfall and after the communities in its path have had to make their preparedness decisions based on the current guidance. This lag between scientific understanding and operational implementation is one of the persistent structural challenges of meteorological forecasting, and it is particularly acute in the current period when the physical state of the ocean is changing faster than the operational systems can be recalibrated to represent it. The models are running with initial conditions that correctly represent the temperature at the sea surface, because the sea surface is observed by satellites with high temporal and spatial resolution, but with initial conditions that only partially represent the subsurface thermal state because the model's ocean coupling components were parameterized in a period when the subsurface anomaly of the current magnitude had not been observed. The storm is revealing the consequences of this partial representation in real time. The specific communities that are now receiving evacuation guidance and preparing shelters and moving the most vulnerable populations to safer locations are responding to the warnings with the specific knowledge that they have accumulated through previous typhoon experiences. The Western Pacific coastal communities that have been regularly exposed to major typhoons over the decades have developed an institutional and cultural familiarity with the preparation process that translates the abstract warnings of maximum sustained winds and potential storm surge into the concrete actions of boarding windows, stocking supplies, and moving to designated shelters. This familiarity is both an asset and a liability. It is an asset because it means that the communities can execute their preparation protocols efficiently once the decision to do so is made. It is a liability because it can produce a calibration of preparedness to the typical major typhoon experience, rather than to the extreme end of the major typhoon distribution that the current storm may represent. The specific communication challenge that the meteorological agencies face with this storm is conveying that the storm the communities are preparing for may be stronger than the storms their preparation protocols were designed for. The best constructed buildings in the coastal communities are designed and built to specific wind speed standards that reflect the local building code requirements, which in turn reflect the probabilistic hazard assessment for the location. If the current storm reaches an intensity at landfall that exceeds the design wind speeds of those buildings, the performance of even the best constructed buildings will be less certain than their occupants expect. Communicating this possibility in a way that motivates appropriate additional preparation without producing panic is one of the most difficult tasks in tropical cyclone risk communication, and the meteorological agencies responsible for the current storm are navigating it with the best available guidance from both the science and the operational experience they have accumulated. The storm surge guidance, which describes the height of the wave of water that the storm's winds will push ahead of it as it approaches the coast, is the component of the tropical cyclone hazard that is most directly life-threatening in the immediate period of landfall. And it is the component whose uncertainty is largest because it depends on both the storm's intensity and its track at the moment of coastal crossing. A storm that arrives slightly north or south of the forecast landfall point, or that is stronger or weaker than forecast, can produce surge heights that differ substantially from the official surge guidance in specific locations. The communities in the warning area have been given surge guidance based on the current forecast, and they are making their decisions about which low-lying areas to evacuate and which structures to shelter in based on that guidance. If the storm arrives stronger than forecast, the actual surge heights may exceed the guidance values in the most exposed locations, and the communities that made decisions based on the guidance may find themselves facing conditions that their decisions were not calibrated for. This is not a failure of the warning system, which is providing the best available guidance based on the current state of the science and the current state of the observations. It is a manifestation of the inherent uncertainty in tropical cyclone forecasting, which has diminished but not disappeared over the decades of research and operational development that have produced the current forecasting capabilities. Every major storm landfall is ultimately a test of the forecast that was produced, and the current storm is a test that is being conducted under conditions, specifically the anomalous ocean heat content, that represent a challenge to the operational models that has not previously been encountered at this magnitude. The meteorologist is still at his station when this account is being written. The storm he first noticed at 2 a.m. has now been intensifying for 60 hours, and the gap between the intensity forecasts from the period before the rapid intensification began and the current intensity is large enough to constitute a significant forecast failure by the operational standards of tropical meteorology. He is not defensive about this. He is, by the description of colleagues who have worked with him through the current event, focused on the current state of the storm and on what the current data suggests about its likely behavior over the next 24 to 48 hours, the period that matters most for the communities that are preparing for its arrival. The data suggests that the storm has not yet reached its peak intensity. The The environmental conditions that have been supporting its rapid intensification, the anomalously low wind shear and the deep warm layer in the subsurface ocean, have not changed significantly over the past 12 hours. The storm structure, visible in the satellite imagery and in the microwave data from polar orbiting satellites that can penetrate the cloud layers to reveal the internal rain band structure, is showing the continued organizational development that is the signature of a storm that is still finding more energy than it is losing. The automated intensity estimates from the satellite data, which provide objective guidance on the storm's current intensity without the subjective uncertainty that accompanies the manual estimates from direct observation, are trending upward. The forecast for the next 24 hours, which will determine the intensity at which the storm makes its closest approach to the communities in its path, is being produced with the specific knowledge that the operational models have been systematically underpredicting the storm's intensification, and with the specific awareness that the physical cause of that underprediction, the anomalous subsurface heat content, has not changed in a way that would expect the underprediction to reverse. The official forecast reflects both the model guidance and the subjective adjustment that the forecasters are applying to account for the demonstrated model bias. And the result is an intensity forecast that is substantially higher than the model guidance would produce if applied without adjustment. The adjustment reflects the specific human judgment that operational forecasting requires and that no automated system can fully replace. The integration of the current observational data with the physical understanding of why the models are failing, and with the experience of watching this specific storm do things that the models did not predict. It is the kind of judgment that 7 years of overnight shifts at the Joint Typhoon Warning Center produces in a meteorologist who has been paying attention throughout, who wrote the understated sentence at 2 a.m, and who has been watching the storm prove the sentence's understatement true every 6 hours since. The storm is still building. The communities in its path are preparing with the information they have been given. The meteorologists who are watching it are providing the most accurate guidance that the current state of the science and the current state of the observations allows. And the gap between those two things, between the storm the communities are preparing for and the storm the meteorologists fear may actually arrive, is the gap that the unusual Pacific conditions have created, and that the forecasting community is working urgently in the hours remaining before landfall to communicate as clearly and as honestly as it can. The Western Pacific is warmer than it has been. The storms that develop in it are responding to that warmth in ways that the models calibrated to a cooler ocean are struggling to fully predict. The storm building over the Pacific is getting stronger than expected. This is what that means. The meteorologist was on his third cup of coffee at 2 a.m. when the model output came in from the latest data assimilation cycle, and the number in the intensity forecast column stopped him mid-reach for the mug. He had been running these overnight shifts at the Joint Typhoon Warning Center for 7 years, had processed the full range of what the Western Pacific produces across every month of the calendar, and had developed the specific professional composure that comes from watching major typhoons form and intensify and make landfall with enough regularity that extreme weather becomes, at some level, ordinary. The number in the column was not ordinary. It was the projected central pressure at 72 hours, the 3-day intensity forecast for the system that had been designated as a tropical depression 36 hours earlier, and that the morning consensus had assessed as likely to develop into a moderate typhoon by the end of the week. The number in the column was not the number for a moderate typhoon. It was a number he had seen printed in intensity forecasts perhaps a dozen times in 7 years on the night watch, and each of those times the forecast had been for a system that was already a significant typhoon showing signs of exceptional intensification. This was a forecast being produced for a system that was still organizing. He pulled up the satellite imagery loop, the sequence of infrared images that showed the storm's cloud structure evolving over the past 12 hours. The loop confirmed what the model was suggesting. The convective organization around the storm center had advanced markedly in the past 6 hours beyond what the afternoon trend analysis had projected. The deep convection, the towers of cloud reaching to the upper troposphere that are the engine of tropical cyclone intensification, had tightened into a more symmetric ring around the developing center. The upper-level outflow, visible in the water vapor imagery as a spreading fan of cirrus cloud being ejected away from the storm's core at altitude, was expansive and well-organized in all quadrants. The storm was doing something that the models, which had been producing moderate intensity forecasts as recently as 18 hours earlier, had not fully anticipated. It was finding the most favorable atmospheric state it had encountered since the first organized convection appeared over the warm water of the Western Pacific, and it was responding with a kind of rapid structural development that meteorologists call explosive intensification when they are being informal about it, and rapid intensification when they are writing the official forecast discussion. He updated the forecast and sent it through the required review channels. He wrote a sentence in the forecast discussion that he later described as the most understated thing he had ever written in his 7 years on the night watch. The sentence read, The system is exhibiting early signs of intensification that exceed current operational model guidance and warrant close monitoring. By the time the day shift arrived at 6 in the morning, the system had completed its first 12-hour period of sustained rapid intensification, increasing its maximum sustained winds by 35 knots during the overnight hours. The forecast discussion that accompanied the morning update did not use the word understated. It used the word alarming, which is not a word that appears often in official meteorological communications, and the senior forecaster who reviewed it before it went out considered changing it and then decided to leave it because the evidence in front of her suggested that alarming was the correct and honest characterization of what the data was showing. The western Pacific Ocean in the region where the storm was developing is not an unusual location for major typhoons. The western Pacific generates more tropical cyclones than any other ocean basin, fueled by the warm, deep waters of the Pacific Warm Pool and by the favorable atmospheric conditions that persist through much of the year in the region.